very special Jason Lim. Jason actually did his undergrad here at Georgia Tech Industrial Engineering, and I see some nodding over there because we used to do research together. You recognize some people in this room. And after that, you went to the University of Michigan to do a PhD there in civil engineering, and has been doing amazing work there since. He's not the only one from our group. We also have Jason with Rabab, forming what I like to call the outpost, all the way up in Michigan. So I needed a cheat sheet because Jason already won so many awards. Today I'll be talking about curved space allocation, but he also worked in transportation systems, on network design. Right when he left Georgia Tech, he won the Informed Undergraduate OR Prize, but since then he also won the University of Michigan Towner Prize for distinguished academic achievement and the COE Distinctive Leadership Award. So without further ado, Jason, please take it away.
Thank you, Kevin. Thank you. As Kevin said, I left Georgia Tech. I graduated in May 2021, right during the COVID, so I had to do the fist bump with President Cabrera instead of the handshake. But I'm happy to be back. It's actually my first time in the CODA building. Actually, Kevin was quite surprised about doing that because I left 21. I think you guys joined here in 2022, and also so I'm glad to give a talk today. Thank you for the invitation. So today I'm going to talk about my research. So it's a collection of my research topics, which will eventually probably be my dissertation. So I hope you guys can give me a fruitful feedback. I'll really appreciate that. So my talk today is titled Mathematical Models of Curved Space Dynamics, Infrastructure, Policies, and User Interactions. And this is a formal title. I actually have another title just customized for AI4OPT, which is referred from the outpost. So actually Jason right here, I think many of you guys will recognize him. Also Rabab, she was a postdoc here last year and she joined as a faculty. So she joined our U of M civil department last year as faculty. So we once in a while hang out with each other. We're keeping the outpost strongly, and we always give. And I think this will be a first, I'll say, a report from the outpost to the main post. So I'll really appreciate again. You guys can give me a good feedback on my. So yeah, let's begin. So I do research in transportation, and I think we will all agree that it is a pivotal part of a social development and connectivity, and it shapes our daily lives by providing numerous systems and services. Historically, it started to serve mass movements through a development of arterial infrastructure. So that's how historically transportation systems were developed. About a century ago, there was an introduction of personal and private vehicles. Since then, people have been using transportation systems to address their individual travel needs. And today, we're seeing another paradigm shift driven by different technological advancements, and we name it the next generation mobility systems, where we have a technology-enabled infrastructure in our mobility systems, and there is a vast majority of a lot more majority of services and modalities introduced in our systems. So as I just discussed, there's unprecedented changes and amid these rapid changes, and these changes obviously brings both benefits and challenges. The pro side is it has expanded mobility opportunities. So in the bottom here, I had a Waymo route a few days ago in Atlanta, and I'm giving a thumbs up to the best Waymo driver. Also, this is the autonomous trucks. I think there's some research going on in AI4OPT regarding the autonomous trucks. UAMs, this is one of my more recent topics I'm investigating, where I try to develop a air and ground integrated multimodal systems. We see scooters and also a service providing a delivery. Basically, this is an example of where the modalities as well as new services are being introduced with the technological advancements. Finally, I hacked into the delivery robot down in Atlanta when I last visited here a few months ago, and basically I was playing around with the robot and trying to hack down the system. So these are the expanded opportunities. However, there also is a downside where this significantly increases the system complexity and scale. For example, this last picture, I hacked into the system. I was just staring down the robot for 2 minutes. Robot couldn't do anything. So, so these are some examples how transportation is evolving, but these bring both the good part and the bad part to the system. So, to summarize my research in one sentence, I designed future-oriented mathematical models for emerging mobility considerations. Because my background is OR, my research is grounded on operation research. I think that's my expectation for most of you guys in this building. So, however, to keep my OR model operational and practical, I integrate many domain knowledge, domain disciplines to boost up the practicability and the realism in my model. For example, there's a various systems, technology-enabled systems such as CPS system or ITS system or different service platforms that provides data abundance. I try to feed those data into my OR, my foundation model, my machine learning model to inform those models with the practical data. I also keep the operational realism regarding transportation because transportation is really highly integrated to humans' lives. We have to make sure that we keep the operational realism and people's behavior. So I adopt different theories such as traffic flow theory and network modeling so I can keep these operational realism. On the more practical side, I adopt game theoretical approach to model a rational and strategic behaviors of different stakeholders in the transportation system. That's a pivotal part because we all have our own considerations and we want to capture all of those dynamics within our model. Finally, I consider social and behavioral considerations that are emerging in our social lives. For example, there are both good and bad sides. The good consideration would be, for example, social equity or transportation equity. We want to provide accessible transportation for all population in our urban setting. On the negativity side, with something like cruising, or congestion or illegal parking where it gives adverse impacts to our systems, and we want to find ways to compete against them and make our system better. So for this approach and to dissect the dynamics of transportation systems, I adopt this so-called tripod approach. So I have three pillars that I always consider when I design these mathematical models. The first will be the infrastructure design. So we want to integrate technology, and these technology-enabled infrastructure becomes sort of a playground of different modalities and services platforms. Second is operational policies. Then we have these modalities and those services. We want to see how they're going to operate so they can incentivize their program and they can provide good services to the system. Finally, the final part will be the investigating user interactions. This is a pivotal part in this tripod approach because ultimately, people are the ones who use these mobility transportation systems, and without understanding them and without informing their behaviors to the model, our models will be essentially useless. It'll be impractical, so we always want to make sure we learn about these user interactions and integrate the critical components into the mathematical models. So then, with these tripod inside, I design mathematical framework. I try to be both efficient and granular. For the efficiency part, I try to identify some parts that can be generalized or can be relaxed to have a more scalable method to solve the problem. But however, especially for the parts like user interactions, we want to keep some granularity in the parts, so we keep those most good components in our mathematical model. And obviously, to adopt these models in a large scale, real life scale, we want to also work on the scalability issues to have a real impact in our social lives. Yes, so for the rest of the talk, I'm going to use the first phase as an illustrative example how to apply this tripod approach in dissecting the transportation dynamics. The first phase has emerged at a critical location that integrates and supports different evolving transportation needs. So this demand has been growing in both volume and diversity because of new modalities and the services, and it serves as a hub or the access points of various operations. Its value comes from providing the best proximity to urban activities, because basically people can park or stop by right next to whatever established equipment they want to go, and they can have the best access to those other services like healthcare, food, shopping, any services that they want to have in the urban setting. So in the bottom left, we see some examples provided by USDOT. What are the new emerging modalities that are being accommodated on curb space, such as EV charging, vehicle storage, that's one of the conventional ones. Food trucks, vendors, ride hailing, flex shown, local businesses, etc. So there are so many modalities that requires curb space access. However, because there was such a huge boost in these demand in the recent decade, the planning sometimes can really messy. You can see this is a picture I took from Los Angeles about a year ago, and you can see there are so many signs that it's not interpretable. So these days are done in ad hoc basis, and I want to design some more mathematical, data-driven policies to operate the space for boosted efficiency and effectivity. So yeah, so I will give you some examples to boost up your understanding. So let's say we have this Mara Reach shuttle coming in to and stop by and drop off the user. You can see there are some spaces available on the curve, but many of them are occupied. However, we see one available space, but historically or traditionally, we assign, for example, this space is assigned for a handicapped parking, accessible parking. However, we usually assign them as a fixed space. If this space weren't assigned for this accessible parking, then this vehicle would be able to park here and drop off the customer and pick up new customers. However, because it currently is operating in a fixed setting, probably this Mara Reach shuttle should have to cruise around or make an illegal stop, whatever it is. But I want to design a smarter way how I can boost up the efficiency of the curve space. So this is a diagram how I illustrate how I envision the future of the curve space operation to be. So let's see, this is a curve space infrastructure. There are some fixed infrastructures, for example, bicycle lanes. This is my first work at Tim. Also, there are some EV chargers placed on some of the curve spaces. However, some of the spaces can be operated in a flexible setting where we can sense the curve space demand real time using a connectivity technology, ITS system, or just pure camera system that we have. Then when we observe this demand, the curve space operator can develop different policies, dynamic policies, such as adjusting the space allocation or adjusting the pricing to control the demand level. Then the users will observe those pricing and also the available spaces, and they're going to make a strategic decision whether they want to participate or drop out from the system. So these dynamic setting can be done in spatial temporal context, where, for example, at the daytime and nighttime, based on the demand compositions and level, the space allocation can be differed to provide best services to the urban roads. I always like to give this another analogy to give you an even better understanding, and this is an exciting one. So I want everyone to imagine a road long of pizza. So you have a group of customers. You want to provide a best pizza experience for those users. People will have different appetite. They'll have different different amount of money in the pocket. So first, what we want to do, you want to cut this road long of pizza into different sizes of pieces, and then you're gonna put different toppings based on people's appetite. And then you're gonna sell those in different prices. For example, if they're aiming for PhD students, they'll probably have to sell it in very low price. However, if Pascal's getting it, probably we can sell it at a much higher price. So this is some of the user consideration they can have on the curve or on the road long of pizza to best accommodate the people's needs. Yeah, so for the remainder of the talk, I'm gonna introduce several of my recent research topics or research projects that revolves around this tripod approach regarding curve space. So for the first two parts, I'm gonna work on how I investigate the interaction of the operational policies and interinteractions by developing a dynamic space allocation and spatial temporal pricing strategies. After that, I'm going to work on how I also integrate in the infrastructure design component in this dynamics by investigating how I can prepare a long-term infrastructure development planning under demand uncertainty. Then I'm going to have a little detour from the OR approach. I'm going to introduce a micro simulation model, how I use to dissect into the user's interaction and learn the behaviors of the users on the road. And finally, this is one of the most recent work. I just completed a preprint a few days ago, actually. And I'm gonna briefly discuss about, if I have time, how I try to regulate the infrastructure or the users' behaviors, so we can have a boost of efficiency in the infrastructure operation through law enforcement. So let's begin. So I'm gonna first talk about the first component, which is about dynamic curve space allocation and basically a dynamic policy being imposed on the curve. So we want to have dynamic and adaptive curve space operational schemes, so we can facilitate seamless adoption and maintain service levels and user satisfaction. So I modeled this game or this relationship with a Stackelberg leader-follower game, where in the game leader, they will decide on the operational policies to boost up their revenue or of their utility. And for the users, we can dissect it, we can divide them into different types of users, and then we're gonna model their strategic behaviors, whether they will accept the policies and accept the policy, and they're gonna reject the policy and drop out from the system. I translate this scheme into a bi-level nonlinear programming as follows. So in the upper level problem, we primarily model the operator, the game leaders of considerations. The objective will be to maximize revenue. They want to generate generate revenue by operating a curve, and then we're going to impose some policy considerations based on their operational constraints. This one less constraint 1M is where it connects the upper level to the lower level, and we are providing this problem phi, the lower level problem, to model the user's behavior in the response to these operational policies. In the low level, we're providing this vector O, which models the operator policy decisions, and by this vector, we're shaping the lower level problem. The objective function is primarily considering the utility functions, the user utility, where the users accept the policy, and the outside option utility, where the users reject the policy. And basically, then we're distributing the users to have the best accommodation based on their traits, which are defined by the two utility, the shape of the two utility functions given by the operator policies. Then obviously this problem can get very messy and can be very hard to solve because of disconnectedness in an inherent bi-level structure, as well as complexity in some of the operational constraints and intractability when you increase the problem to large scale. To overcome these challenges, I apply a series of solution methodologies. So for the disconnectedness, I do a KK theory formulation where I append the lower level problem to the upper level problem, making it into a single level reformulated model. After that, I do some tricks to convexify the problem, then which becomes a single level convex model, which serves as a benchmark method to enable us to use the state of the art solvers like Rovio or sequence. However, to operate this benchmark model in scale is still challenging, so I imposed a Bender's decomposition solution methodology to enhance the scalability of the model. So Bender's decomposition, assuming many of you will be aware of this method, where we apply a divide and conquer method where we partition the problem into a subset of constraints, and we're gonna solve them iteratively so we can facilitate the solution finding by exhibiting a better solution time on each component of the part, where they're combined, it's much harder to solve at scale. So in the master problem, we're going to update the policy to denote good candidate solutions of the policies, and then we're in the sub problem, we're going to provide a mathematical approximations of how good or bad those policies are based on the user's reactions. However, in the paper, I also designed an alternative method called the Bender's inferred valid inequality cuts algorithm, or in short, I call it the Vivek algorithm, and that's I call it the Vivek algorithm. And in that method, I leverage the fluctuating efficiency in the Bender's decomposition iterations. So I take a two-phase approach. The first, I solve the model in the Bender's decomposition fashion, and I store all the Bender's cuts, the Bender's cuts in the form of valid inequalities. And after a fixed amount of iterations or amount of time, I'll then retain all the cuts and append that in the benchmark model. And in the cutting plane fashion, those Bender's cuts will serve as a very effective cutting planes and reduce the problem scale and facilitate the solution solving much quickly. So this diagram also introduces where first we're gonna do Bender's decomposition, generate Bender's cuts, and at certain time or certain iterations, we're gonna return to the benchmark model with all those Bender's cuts of valid inequalities that retained, and that will facilitate the problem solving much more quicker. So I do a series of experiments where I have different usage types of, specifically I consider 4 modalities, and these modalities all have different user traits. And about the utility functions, I say for the users in general, people will be more favorable if the price is lower or the congestion is lower. And for the outside option, they don't really care about pricing because they're just simply dropping out. However, as the congestion or occupancy goes up, they will be more inclined to drop out because they're having a harder time in searching the curse space. So first, let's talk about the methodological side and see how this Vivek algorithm works. So we can see, here the gray is the benchmark. So the single level reformulation. The blue is where I just do Bender's decomposition for the entire time. And this Vivek algorithm is where I do the two-phase approach, and this vertical dotted line shows where there's a phase switch. So you can see when you compare the gray and blue, there's a very different trend. When you just put the bottle into the MIB solver, you can see it is very effective in finding a feasible solution, but you can never prove optimally. It is having a hard time reducing the duality again. Benders decomposition, however, is very good at reducing the solid feasible region, but it is having a slow convergence and denoting the feasible region in a good timely manner. That's why I imposed the two-phase method where I first with the good Bender's cut, the Asabella inequalities, I'll quickly reduce the feasible region of the solution, and then I'll employ that advantage and try to solve the benchmark model in a much more quickly and efficient way. Also, I have some operational observations from my experiments. I'll just give a brief summary about them. Regarding space allocation, we want to have we show that our method is enabled to give a demand responsive space allocation, so we can have less marginalization of the users, as well as the more interesting part is people, the operator actually decides sometimes to keep some spaces empty, which are denoted by these lightly colored bars, where they strategically keep some spaces empty to manage their occupancy levels, and they can provide more uniform service to all different users. And for the operator's utility, which is the objective of the model, we see the people's sensitivity to congestion or discomfort has a larger impact on utility than sensitivity to pricing. So this was also an interesting observation from the paper. So then now let's go to the second part where I delve into a pricing strategy of the curve space. So if you think about even Atlanta, we see uniform pricing for many infrastructures. People will get upset with my pricing here is more expensive than my pricing that will be offered 2 blocks away. So just to reduce that confusion, people like uniform pricing. However, I thought about whether this uniform pricing strategy is adequate for curve space setting, because the demand composition can very differ by what types of establishments are there in our urban setting, or by the time or where the businesses are located, etc. So I investigated into spatial temporal pricing, where I want to see whether lower pricing will promote relocation of the users. So for an operator, they can manage the demand levels, and for the users, they can find good alternatives in the better pricing. So I imposed 3 pricing policies. So first is a temporal pricing, where I will have dynamic pricing only based on temporal manner. Or like, for example, in the morning rush hour, the pricing will go high. In the nighttime, the pricing will go low. Subsidy pricing is next, where I utilize some of the domain knowledge that I know about different spaces, and I will strategically reduce or deduct this price for certain locations at certain time with the strategically informed information. Finally, the most flexible one is the spatial temporal pricing, is that we don't provide that domain knowledge. We just let the solver or the model to decide on what is the best pricing strategy at different locations at different times. So I first tried to solve this problem with the Vivek algorithm, or Bender's decomposition algorithm I introduced previously. However, it wasn't as effective because obviously we have more consideration integrated. The disaggregated cuts doesn't work as well. So I had to come up with a new algorithm based on Lagrangian relaxation. So in this method, I'm also pretty sure many of you guys will be aware of this method, where we identify some so-called completing constraints, which is harder to solve, and we will dualize that constraint and give a penalty of not being able to match that constraint. I wish Jorge to be in this room today, because I was actually motivated this method through his talk 2 years ago at Informs. So unfortunately, I guess he couldn't make it, but please extend my thanks to him when he comes back.
He's on internship. He'll be back next week.
Oh, please extend my thank you to him when he comes back. Yes, so the classic Lagrangian relaxation method, where I solve the relaxation problem, I'll update the solution upper bound, then I'm going to solve the feasibility problem to check the feasibility of the solutions obtained, and check the so I can retain the final solution that is feasible in every setting. And then I'm going to update the solution upper bound and have this iteration for a number of times until I reach the convergence and denote the optimal solution. So then this method is to check the efficiency of this method. It is surprisingly, strikingly quicker than any of the methods I've developed so far. So here the dotted line shows the benchmark when I just solved the MIP with the solver, and the solid line shows when I use this LR method. You can see the optimality gap shown in the vertical axis is dropping much more quickly, significantly quicker than when I just use the solver. And I didn't do a direct comparison with the Vivek algorithm that I used previously, but from my experience, I know it takes at least an hour to solve any instance in a good quality. And now you can see the convergence is much quicker. In most instances, they're stopping before 30 minutes or even 15 minutes. So you can see this LR method is showing a quicker solution convergence and also a narrower solution variance across randomized instances.
Are you still able to calculate optimality gaps? Because
Yes.
you don't get bounds anymore, right?
That is true. So that is one weakness, but that is one weakness. That is true, but because while I was thinking, we always check the feasibility of the problem, right? And when we do that sanity check, it always passes the sanity check. So we weren't that worried about the optimality gap because ultimately what we want is the good solution that can be applied to the society. Yeah, so this is one example of a spatial pricing. This is the simulated results, so it's not representing any real life settings. So just to give a demonstration, tempo pricing, all unit pricing at the different times. Subsidy, we know this zone 3 in dotted green, indicated dotted green line has a lower demand, so we're giving a lower price. Spatial temporal pricing, we're giving full flexibility of pricing to the model. So you can see here, these three heat maps right here is showing the utility or the operator's revenue when you have tempo pricing, subsidy pricing, and spatial tempo pricing. And the bottom ones are comparing the pairs of them. And the red is showing there is a increase in the attribute that we're comparing. You can see when we have more relaxed pricing scheme, we can see the utility will always go up, shown in the red sense. So that's one advantage. However, when we consider users' considerations, that's not always the true. And that is because we don't necessarily consider the user's interactions or users' behaviors on the upper level model. And because we are only optimizing the upper levels objective, there's sometimes the case where when we apply more relaxed or more sophisticated pricing, it will hurt the user's utility. As such, I try to enhance their experience as well in this model, and it can be done in a relatively simple manner by adding some linear terms into the objective function of the benchmark model or the MIP model. So here, for example, we are adding a coefficient where we want to keep some sort of retention of the users. So we're enforcing to keep some level of enforcement into our model by having this linear term. Now, regarding the allocation volatility, we're calculating the volatility of allocation between time intervals, and this is motivated by if there's a two dynamicity in space allocation, people will be confused by the policy imposed, and this could long term hurt their utility or experience at the curve. So we want to keep some volatility. We want to keep the volatility low if in a possible case. So we are subtracting the penalty term imposed by the volatility of the infrastructure. Then you can see when we compare each of the pricing schemes, not only spatial temporal, but all pricing schemes, when we add these simple linear terms, you can see there's no practical sacrifice in operator utility. You can see most cells are in gray, not all cells are in gray, meaning there is not many percent difference. However, regarding the user's consideration, you can see that, for example, the user's retention are significantly increased when we impose these simple linear terms into the objective function. And in the right case, we can see the volatility will be significantly reduced while maintaining the same level or no sacrifice utility in the problem. So this means we can always search for the alternative equilibria between the operator and the user, between the two players. And by accommodating all the different considerations, we could converge to the real social optimal solution that we want to have in our society. So until now, we talked about a static setting where we say we know about the demand. We know at this time, at this location, we have this expectation of demand to be realized. However, in the long term, that's not always the truth. We cannot when I was at Georgia Tech, I never imagined this building to be here. For example, so like that's even like 2 years term. Like if you want to prepare an infrastructure design for 10 years, 20 years term, we want to have some strategic planning. So now we're moving into a stochastic setting of demand where, okay, we don't have a perfect information about how the current space demand will look like in the next 10, 20 years. But then we want to develop the infrastructure and prepare the infrastructure proactively. So when those demands emerge, we can serve them at our best. So we want to seek a balance when we design the infrastructure development. We want to seek a balance between the permanent installations that require money and some of the spaces that can be allowed for dynamic services. Also, we want to know where and when to invest for the infrastructure upgrade given the budget constraints. And so obviously the challenge is we don't know about the future demand, and the pace of these technological advancements that brings these demand changes are uncertain. So here, this is a picture of how people decades ago envisioned the transportation system of year 2000 would be. Some are true now, some are still not true. And obviously it shows these depicts how people always estimate the demand wrongly for the future. So to see the relationship, because we have an uncertain pace of the technological advancements, the user demand composition is uncertain, then the current space utilization in the next 10, 20 years will be different, which will impact the investment payoffs that we develop today. So to overcome this challenge, I pose a two-stage stochastic optimization model where we try to overcome this uncertain future demand levels and compositions. So in the first stage problem, we develop an infrastructure development planning. So the first set of constraints is about development decisions, which I model with a network flow of decisions. So each set of these yellow, orange, and red cells are the modalities. So what types of for each space, what types of modalities that space can accommodate with the infrastructure upgrade, and these vertical ones shows the different time points. So you can say like 5 years, 10 years, 15 years, 20 years. So we have a network flow model deciding the development decisions. Then each of these arcs have a development cost. So we are calculating the development cost using this variable data, which is comprised of the variable cost, fixed cost, and the one-time electrification cost. I consider the electrification separately because it is very costly upgrade to have it in the urban setting. The last is the development budget. No, I wish we have infinite money. That's never happened. That never happens. So we have this budget constraint where our budget is constrained by BT for each time period, and the total budget is constrained by B. So this development cost is contained in the upper level or the first stage objective, and now we see the expectation of the lower level problem or the recourse problem, where we evaluate the quality or the return from these development decisions at different time periods. The recourse problem is as follows. First, we have the supply of spaces for different modalities based on the decision vectors X, the flow variables. We sum over them and see at each time how many spaces we have for each modality. And the demand, the uncertain demand shown in D tilde is showing what is our expectation of that some type of demand at certain time. And if you look at the structure of this program, it is a transportation or assignment problem where we have a set of supply nodes, set of demand nodes, and we're distributing them with this U variable to see what is the best assignment or how many users will be able to use, while how many people will be forced to drop off because there's no sufficient space, etc. And because of these the summations over P prime, which contains a dummy set that captures either user attrition or dropout users, we can argue that this problem has complete recourse, which makes this problem much easier to solve. So then now let's consider how I solve this problem. First is simple average approximation, which allows me to replace the uncertainty set with the multicolor sample, so I can have an estimation of the original distributions of the uncertainty. Next is path-based reformulation, and this is a unique way that is not conventionally used in solving stochastic optimization models. So here, this is a network flow model I've introduced. We can see as the number of modalities grow or number of time intervals grow, the number of the flow variables will increase exponentially. So what we do is, instead of modeling each of these flow variables, we're going to model them in path variables. say we know these sequences of how we develop it, and we're gonna try to come up with how we can devise a good development sequences, I call it, for the long period of time. This itself will not overcome the scalability issue. However, it becomes a good foundation for a column generation method, which allows us to introduce new candidates of highly priced paths into our model, and which enables us to only consider a good candidate development sequences in our model. So basically, we'll generate a series of Monte Carlo samples. We'll solve a column generation problem where we introduce the new path variables until we identify no path variables with a negative reduced cost. We reinstate the integrality of the problem. We solve the feasibility problem to check the recourse of the problem. And then we do this for a number of times until we know a good quality solution. Also, I add one additional small extension to the method, which is a column dropping procedure. And this is motivated by when we obtain an integral solution, there will be only one active variable. Even if we have notified a good full path variables in the fractional setting, ultimately there will be only one path variables that are active and the remaining will be inactive. So what I do is when I conclude this column generation procedure, I see all the I check the current values or the dual values of all the path variables introduced. Some could be, even though they're introduced as a originally highly priced variable, they can be later priced up and they can become zero. I simply drop them, which will further reduce the problem scale with a small compromise of the solution quality. Because when we reinstate the integrality, that priced out variable could be a good best solution. So there could be a small compromise, but ultimately I showed that that compromise is good enough to us to keep it. So I introduced a set of experiments. I considered 3 modalities that requires permanent infrastructure development: EV charging stations, micromobility stations, and transit stations. They require some installations and some developments on the roads, whereas the flex shells will be able to have some dynamic setting, just as in my previous projects, to have a dynamic operation of the space. So yeah, let's first talk about column generation efficiency. So regarding solution quality, the gray is the standard SAA method. I just do a Monte Carlo estimation through SAA method and just solve that with the benchmark solver. The blue is when I do SAA-CG method, and the sky blue is when I do also integrate that column dropping procedure. When the gray is hard to see because they're directly overlaid on the blues, so they have practically no difference in solution quality. There is some small compromise in solution quality when I add that the column dropping procedure. However, the solution time differs a lot. You can see the rate of increase of solution time will happen more quickly when we use the benchmark method compared to the red when I do the column generation, and when I do the light red when I do the column generation and dropping procedure. And here forgot to mention the horizontal axis shows the problem scale. So as you have more n, the problem gets harder to solve. So to summarize these observations, when we compare the relative difference of different attributes, you can see the profit difference between the 2 column generation based methods, the benchmark methods. The profit difference is negligible, is almost 0. However, there's a good decrease in runtime, which allows us to have more iterations of the sampling, and it increases the chance or probability of denoting a better solution. I want to also mention about some practical insights driven by these the stochastic optimization model. First is about the profit through budgeting. So here in the heat map, the horizontal axis shows a total budget allowed for time horizon, and the vertical axis shows the budget allowed for each time period. So the vertical axis can be translated into budget flexibility. So when we first talk about, and the sales obviously shows about what's the expected profit in a long term, or when we keep these infrastructure planning for the long period of time. So first, when we talk about the profit, we can see the marginal profit will diminish it as the budget increase. And this is an intuitive observation because we have a fixed number of spaces. And when we at some point when we have optimal planning for all the spaces, adding more budget will definitely not help us. But a more interesting observation comes from here when you compare this cell and this cell in particular. This bottom right cell has 3 million total budget, but has a very rigid planning of just allowing $1 million per time period. This cell has a $0.5 million less budget, but it gives a $0.5 million greater flexibility. We can see the utility or the profit obtained in this cell is greater than this cell, meaning even with a lower total budget, the flexible budgeting will facilitate a higher profit generation. And this trend was shown for, this is one example of the instance I calculate, but for different scenarios, this was a uniform trend. The next is about how we use the budget. So now the cells are showing how much budget are being used in total to have the optimal planning. We can see first, similar to the previous observation, after having with the total budget of $3 million, we will not necessarily use more budget because our planning is already optimal. Also with similar to the previous observation, the flexibility in budget allocation, comparing these two cells, we can see allowing more flexible budgeting allows us to use less amount of budget to have an improvement planning. And if you compare these two cells, you can see wrong direction. You can see the profit here is much greater than the bottom cell. But now you can see but that higher utility was obtained with lower budget. So this is double good for the system. So finally, I have a little amount of time, so I'll briefly go over the non-OR part, I'll say. So then one challenge I had in my research program was that it's really hard to understand the user's behaviors. And why is that? Because there's no good real data set. We have data sets for individual operations, but we need something that captures the dynamics between those modalities. But those are really hard to obtain. So I have worked on developing a micro simulation model that allows me to have a customized setting to operate my experiments and gain some insights about the curve space behaviors. I use this software called Sumo, which is a freeware. It's freely available for everyone. Also, our source code is available on GitHub right now. So if you're interested, feel free to take a look. So I had a recording, but Wi-Fi is slow, so this will happen. So instead of me going through the slides, I'll just conclude my talk by showing some recordings. See, I have a recording here. So for example, this is one example how I model double parking behavior on the curb. So this vehicle right here, I started the double parking. I had to define a dummy zone or dummy space to have to model double parking. You can see this a corridor has been indicated in red, and we're having a significantly reduced speed over velocity because of the double parking vehicle impeding the road use of the other users.
Where's the double parking?
So Sumo does not have a good feature to directly stop the vehicle on the road. So we have to define these dummy spaces to model the impedance of the traffic by the double parking behavior. So another example is, I have it in the next tab, where this is called unauthorized parking. So this is a green delivery truck, and this will make a left turn. Yeah, left turn. And let's see. These 5 spaces are assigned for. It's a little slow. Okay. So let me stop here. So here, this vehicle is trying to look for a loading zone to drop off their delivery. So when the vehicle comes in, so now you can see this red vehicle. This is a regular street parking vehicle. Is occupying a space assigned for the loading zone. So this is an unauthorized parking. It is using a space with a mismatch usage. had this vehicle was not there, that delivery truck would use that space. But because there is that illegally using space, the vehicle on the space, the truck has to pass by, which will increase the congestion and discomfort of the users. So these are different dynamics I tried to model on the curve space sumo model. Yes. So then I'll skip the experimental results because but I can tell that many of these insights are integrated into my modeling, and especially when I shape the utility functions of the models I use in my models, I try to integrate these insights to enhance the behavioral realism in my models. So the last project, really briefly, then okay. Now I consider illegal parking, for example, illegal behaviors. We want to see the ways to regulate them. Those are basically bringing adverse impacts to our society, to our roads. So I want to talk about how I can control the misuse of those spaces. So then, how I do is I integrate another player. Originally, I had a two-player game with the operator and the user. I add a third player called regulator. So so you can think of, like, for example, like a government or the police agency. They're trying to enforce law enforcement on the roads. This three-player game is a much more complex dynamics compared to the two-level game. So I adopt a multi-objective bi-level optimization problem where I try to solve a perimeter front of the different relationships of the policies and compare the societal impacts of different law enforcement levels imposed by the government or the regulator. So to summarize, I've introduced my structured tripod approach where I consider infrastructure design, operational policies, and users' interactions. So this becomes the foundation of dissecting any transportation systems that are existing in the world. I use a curve space as an illustrative example where I provide a technology-enabled dynamic operations to enhance the efficacy of the system. And then I used data information and integrate user behavioral insights to enhance the behavioral realism of the model. Then also I also consider the methodological side where I try to enhance the scalability challenges, or compete the scalability challenges, as well as try to provide some practical insights regarding curve space operation through my dissertation research. So the real reason I'm here today is I want to announce that I'm entering my job market this coming year. So I am here to promote myself. So I hope for the remainder of today, I'll love to have good conversations with you guys and build new connections. And yeah, so, and again, I'm really happy for this opportunity to return to my home institution. I mean, really, my research here really motivated me to start PhD. And I'm just really grateful especially for Kevin and Hong Zhao, but for people who were here when I was there, but still for the remaining members of AI4OPT, I'm really happy that you guys are keeping the heritage for me. This is the end of my talk. These are my contact information, so feel free to connect with me through LinkedIn or through my website. And if you have any questions, we have 10 minutes left, so I'll open the floor for questions. Thank you very much.
Great. Great, we have time for questions and discussion. Who wants to go first? I mean, I will.
Oh, please.
Oh, you have one? Yes.
Yeah.
Maybe a simpler question. So if I'm building a new city block, what would you say is an optimal curve design as a designer?
So like that is a good question. So curve design, like how the infrastructure should be shaped. You're talking about like curvature and all that. Are you mentioning about that? So I don't specifically consider that into my design. I talk more about the operational scheme. However, there are some research results about them. For example, whether having so it's called a complete street concept. I don't know if you're aware of that. What types of infrastructure or how the lane should be shaped. Is it having a protected lane rather than having additional like traffic lane? Which one's better? I mean, they do that kind of research. It really is a really case by case. In some cities or some urban settings, it's better to not have the protected lane, like the orange cones and have an additional lane for the enhanced throughput. For some spaces, it really goes with different social to components like demographics, what types of users there are there, like what time the demand is spiking, all that. I've never tried to model that mathematically. I mean, through a optimization model. But I think that's a very good, interesting approach. Actually, I'm glad. Oh, actually, there is one research done by Professor Hani at Northwestern, who passed away a few weeks ago. He had a choice model, basically, where you have different settings: 3-lane, 2-lane with the protected bicycle lanes, 2-lane with the protected cones and the bicycle lane, etc. So there are different arrangements you can have, and they're running a choice model to which choice will best help in that particular setting. But I think that really comes with a it's really a customized approach for each of the settings. If that answers your question.
Maybe an offshoot question, so fixed price street parking, do you think that should all be variable, like auctioned out?
Fixed price. Okay, so there was historically in the US, most street parking was free parking. Free. So then there were different researchers. They're saying that is horrible. They should never do that. It just boosts up the demand without any regulation. So it'll just make the road very messy. Then people started to do fixed pricing. It actually works quite well in most settings still until today. But what I'm envisioning the future is when you have all the connectivity, like I'm really provisioning the next generation of the infrastructure. Like say, for example, like when you call Uber, we just observe the price through our app. Like we won't be like write down the price, do the calculation, and try to see whether me going 2 blocks further will make the price cheaper. But when we have the connectivity enabled in our infrastructure, say you're driving a Tesla, and Tesla is by itself selecting where to park, and when the vehicle can observe that information, in a very seamless way. I mean, you have no effort to do. I mean, it just knows it, right? Is that connectivity technology enabled? Then you can say this, considering the pricing as a variable can be an option because it really doesn't hurt people's experience. For now, it could be a little early because people won't be informed as practically or efficiently as the connectivity technology will enable. So here in my research, I especially for the first two works, I really are trying to set a foundation for the future operation with the different penetration rates of the autonomous or connected vehicles.
Okay, so please, I'm very curious because you, especially for the first one, the dynamic curve resource allocation, solve these massive mathematical models. Still takes a bit of time to do that, right? An hour or 10 minutes or
Correct.
So I'm very curious to hear your thoughts on, do you think there's any value in a system that just updates the prices every 5 seconds? And if so, how are we technically gonna get there?
That is a good question. So, correct. So there's always a trade-off. Obviously, in a mathematical perspective, if you give more flexibility, say we allow price adjustment every 5 seconds, probably will give us a better solution. Like, I mean, no worse solution, I would say, mathematically. However, given that we can solve in a good optimality, get good quality, given that having more relaxed constraints or relaxed consideration will give a no worse solution. However, in transportation, because it's so highly integrated into humans' life and humans' perception of those information, it is not ideal to do that because, as you said, if you change your price every 5 seconds, people will start to probably hack the system. Like the delivery robot example I gave you, they'll just refresh every 5 seconds, and they'll actually increase the congestion and the adverseness in the system. They'll just wait until check every 5 seconds, 10 seconds to see wait until the price drops to the golden level they want to have. So I think that is I think very challenging, I think, social tool problem, not just mathematical, because really we have to know how people perceive those different pricing or different policies on vast list of criteria. We have colleagues where, like, for example, like Professor Pat Mokhtarian from CE department here at not Michigan, Georgia Tech, where she is a superstar in those travel behavior survey methods. We do rely on those researchers of, hey, what do you think is so we want to have dynamic policy. So what's the good scope of dynamicity we want to impose in the system? Because more than that, it will just confuse more people. It will do more harm than the good. So always want to try to seek the balance, but my research really aims for preparing the model. Like if we have the model and if we know those behavioral or those considerational traits, then we can easily integrate into the model because the math is ready. So I think really my research focused on developing the model and proposing the model to the Transportation Engineering Society. And always, that's why I always seek for collaborations or discussions with different colleagues, so I can seek a good balance and find the sweet spot between the mathematical or methodological advancements and the practicability of the model.
Great, thank you. Any final questions? Zhao, Ryan, all good? Okay, well, we'll leave it there. Thank you so much.
Thank you.